Okay, another example, we're given a function 3x minus 6 cosine x, restricted at the interval 0 to 2 pi. We want to determine the concavity of the graph and also find any points of inflection. So we start by finding the second derivative. So we first find the derivative to be 3 plus 6 sine of x. And then we find the second derivative to be 6 cosine x. Remember, to find points of inflection or concavity, we do basically the same thing with the derivative that we would have done, the second derivative that we would do for the derivative. We're finding increasing and decreasing behavior. So we figure out when is the second derivative undefined. In this case, we're doing a cosine function, which is defined everywhere, so it's never undefined. When would it be 0? Well, we'd find out when is 6 cosine x 0. Remember, cosine is 0 at 90 degrees or pi over 2, and also at 3 pi over 2. So we have two values of interest here at pi over 2 and also at 3 pi over 2. We would then plot those values on a number line. And test the derivative in each region that's created. So it would be here at pi over 2 and also down here at 3 pi over 2. Keeping in mind here also that because we are restricted to the interval 0 to 2 pi, that we have those endpoints cutting us off. So we need to pick something that's between 0 and pi over 2. Well, a very easy choice here might be pi over 3. Something between pi over 2 and 3 pi over 2. Evaluate f double prime at, say, pi. And then finally something between those two. I'm just going to choose 5 pi over 3 because it's easy to compute. Well, 6 cosine x, 6 has no effect. Cosine of pi over 3 is 1/2, so 6 and 1/2 would be 3, meaning that we're positive here. Cosine of pi is -1, times 6 would be -6, so we're negative here. Uh, 5 pi over 3, it's in the fourth quadrant. Reference angle is pi over 3, so it's again 1/2 times 6 would be 3. It's positive 3. So it's positive between 0 and pi over 2, and 3 pi over 2 and 2 pi. It's negative between pi over 2 and 3 pi over 2. And finally, we take these results and we use them to talk about concavity. Remember, when its second derivative is positive, it's concave up. Second derivative is negative, it's concave down. So we can just go over here and say that the graph is concave up on the interval 0, on the interval 0 to pi over 2, and then also on the interval 3 pi over 2 to 2 pi, and it's concave down. On the interval pi over 2 to 3 pi over 2. The last question that we're interested in is points of inflection. Points of inflection are points where the concavity changes, provided they're points on the original graph. Well, those two values, pi over 2 and 3 pi over 2, since the original graph is dealing with cosine and just x, the original graph is going to be defined at both of them. So both those points are for us points of interest. And the concavity does change. So both of those are points of inflection. We can say that we have points of inflection.
Dad, look.
Points of inflection. So at both pi over 2 and at 3 pi over 2. And it's just a matter of evaluating the function. At pi over 2, we have 3x, so 3 times pi over 2. Cosine of pi over 2 is 0, so it's just 3 pi over 2. So pi over 2. So pi over 2, 3 pi over 2. Again, evaluating the original function. And when you plug 3 pi over 2 in, you'll have 3 times 3 pi over 2 would be 9 pi over 2. Cosine of 3 pi over 2 would be 0. So we get the other point of inflection would be 3 pi over 2, 9 pi over 2. Okay, now we found our points of inflection. So we found the concavity and the points of inflection.